So this is a short video lesson on the 1.6 notes, classifying polygons. Again, these notes are going to cover a section that is actually outside of Chapter 8, but we put it in with Chapter 8 so it helps us better understand 8.1 when we start talking about classifying polygons and determining their interior-exterior angles. So let's go ahead then and look at our first definition here. A polygon is a closed figure formed by a finite number of coplanar segments such that the sides that have a common endpoint are non-collinear each side intersects exactly two other sides, but only at their endpoints. So a lot of different things are happening there. Just make sure that it's closed, meaning that when I look at my set of vertices, no matter how many there really are, that the segments touch only at those endpoints, and it's completely closed in shape, so that I could actually fill this square up with something, right? Or this shape, I could fill it up with something. That makes it closed. Every endpoint is only touched by two segments. Only two, and it's only at their endpoints. If they are collinear, then it's no point of having a vertex, because if this was collinear, it would just keep on going, and that wouldn't make a vertex. It's got to change direction. So within that polygon family, we have two different types of polygons, the convex and the concave. Convex, no lines contain a side of the polygon containing a point on the interior of the polygon. As I draw a figure that would be convex, for example, this pentagon, when I go ahead and draw those segments, none of those segments are going to contain a point in the interior of the polygon. So when I draw this line, not on the inside, 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 always on the outside or on the edge or the segments of that polygon. Concave is when I do have interior points. So let's draw a concave polygon. Prime example of a concave polygon. And I'm okay for a while, but once I go ahead and draw this segment right here, this segment can then extend and exist in an interior spot, an interior value of the polygon. So if you could do that for one of your segments, then obviously it's going to be a concave polygon. Regular polygons have to be a convex polygon where all sides and angles are congruent. So let's just draw an example of a regular polygon where all the sides and angles are the same length. So here I have a square, which is a regular quadrilateral, where all the angles and sides are the same length. Same would be true for an equilateral triangle or equiangular. All angles and sides are the same length. An example of an irregular polygon, irregular where not all the sides or angles be the same length. For example, something that might look like an arrow pointing up. This is a closed polygon, however, not all the sides and angles have the same length. Also, it's concave. This is a unique one. That is a rectangle where the opposite sides are congruent, but the sides adjacent are not congruent, and all angles are equal to each other. So here we have a case of where the angles might be all the same measure, but since the sides are not all this congruent to each other, that would be considered an irregular polygon. So when we classify polygons, it's going to be by their number of sides. And here are some just classification names. A lot of them you've heard before in grade school or maybe in middle school. A three-sided figure is called a triangle. Four-sided figure, most general term, is a quadrilateral. Five-sided figure is a pentagon. 6 is a hexagon. 7 would be a heptagon. 8, octagon, or stop sign. A 9 would be a nonagon. 10, a decagon. 12 would be a 2, deca, 10, dodecagon. And then any time that's larger than 12 or 11, we can just use the number of sides, n, and then do dash gon. So 14 gon, 15 gon, 16 gon, 30 gon, really, anything. Determine if the figure is a polygon. If so, classify convex or non-convex, which would be concave. This one, yes, polygon. Number 2, not a polygon because I have one vertice that shares 4 segments. So this is not a one single polygon. Polygon, polygon, polygon. However, number 4, not a polygon because here I have a curve. So it has to be made up of segments, and curves are not considered segments. Looking at the yeses, this would be convex. Because again, all my lines are on the outside of the figure. Number 3 here, since that line cuts through my object and breaks it up, that's going to be a concave. 6 here, that's a convex. And 5, if I take this segment right here and I extend it, it cuts through the surface, so this would be a concave. So we're going to try a couple more practice problems on the next page, and then hopefully you'll have a better idea of how to classify polygons and name them. So here are 8 through 13, some practice problems. We're going to classify the polygon by their number of sides. Once we do that, we're going to tell whether the polygon is equilateral, equiangular, or regular. If you remember from previous lessons, equilateral means that all the sides are the same measure, equiangular means that all the interior angles have the same measure, and regular means that it's both equilateral and equiangular. So go ahead and pause the video at this time and go ahead and try 8 through 13. Give it your best shot to classify these polygons, and then you can follow along afterwards to check your work. Number 8, if you're looking here, you can see that we have some arcs and tick marks, and since those go all the way around the figure, that tells me that 1, 2, 3, 4, 5, 6, 7, 8, this 8-sided figure is equilateral and equiangular. Therefore, it is a regular octagon. Number 9, they tell me that all the side lengths of that 5-sided figure are 1 inch long, so that means all their sides are the same length. They also say that all the angles are marked as congruent. So this would also be a regular figure, and it would be a regular 5-sided figure, so that would be a regular pentagon. Number 10, I have a triangle here that's equiangular and equilateral. So we could call it an equilateral triangle, but with regard to our new terminology, let's call this a regular triangle. Number 11, since all the sides are not the same length, and if these two angles are congruent and this one is not congruent to those two, this is neither equiangular or equilateral, but it is a triangle, so we'll call this a non-regular, or actually the correct name would be an isosceles triangle. Since we learned that in a previous chapter, I thought we'd apply it here. Number 12, here we have a quadrilateral 4-sided figure where it looks like I have 4 tick marks, so that makes all 4 of those segments the same length. But the angles do not have the same number of arcs, so that means it's not equiangular. So this would be an equilateral an equilateral quadrilateral. Definitely a mouthful there. You gotta make sure you be careful with that one. Equilateral quadrilateral. If you're familiar, you might have also recognized if all the sides of a quadrilateral are the same length, this is also called a rhombus. And that will come up later on in this chapter. Number 13, here we have a four-sided figure. All angles are all right angles, but not all the sides are the same length. Equal angular, but not equal lateral. So this would be equiangular. Quadrilateral. And if it's equiangular and it's a quadrilateral, then it must be a rectangle. And again, that will come up later on in this chapter. So that's the end of 1.6. If you have any questions, please rewatch the video. Come talk to me in class, and go ahead and try the practice problems.